So we're going to talk about white balance. As we're going to mention in the sound workshop, the speed of sound in dry air at 20C is around 343.2 meters per second. The speed of light is around 300 million meters per second. So do you know how far away the sun is from the Earth? Normally it's measured in light minutes. It takes 8 light minutes for light from the sun to reach us here on Earth, which means that if the sun explodes, we won't know about it for another 8 minutes. What we perceive as light, which comes from the sun, is only a small portion of what we call the electromagnetic light spectrum, which ranges from radio waves to gamma waves. And as you can see there, the visible light section is very small in comparison to all the waves that come before and after. Little fun fact, you know how sound is transmitted over radio signals, right? Where you get those radios and you tune them in and you listen to that, right? Do you think that these waves are coming in at the speed of sound? No, they're not. They're coming in at the speed of light because they're part of the electromagnetic light spectrum. Radio waves carry within them an encoded signal, which then is decoded by the radio device back into sound. But all of that, even your cell phones, they're all traveling at the speed of light. So again, we go back to the visible light spectrum, which is just a small portion of light. And it ranges from red to violet. If you take a light and pass it through a prism, a white light, which is a combination of all the colors, it'll diffract and break out into its component waveforms from red to violet. Cameras don't understand what white is, and what we perceive as white is not exactly white because it could be tinted to blue, red, or any other color. That's because light has a temperature, and depending on what medium it's passing through or what medium is emanating that light, it can have a different color temperature. So, candlelight would be somewhere at 1,500 or 2,000 Kelvin, and Kelvin is the measurement with which we measure the temperature of light. The household light bulb, which we normally use, is around 3,200 Kelvin. Noon daylight is around 5,600 Kelvin. An overcast light is around 7,000 Kelvin, and a totally blue daylight is around 10,000 Kelvin. Now notice how we go from warm to cool colors, except that temperatures go from low temperature in the red to higher temperatures in the blue or violet. That's just how it is. We perceive blue to be a more cool light, but it's actually more of a hotter light. It has a higher temperature or a color temperature. Whereas red, we perceive it as warm, but it's actually has a lesser temperature or a lesser Kelvin temperature than the rest of the colors.
What is color? Color is the result of light being reflected off an object, solid, liquid, or gas, or whatever, at a different wavelength than the original light because of the properties of the object to absorb other wavelengths of the electromagnetic spectrum. Meaning, if we have white light coming from the sun or any other source, that is at 5,600 Kelvin or more, well, we'll get into what that means later, but let's just say that visible light from the sun is hitting a fruit, an orange fruit. A fruit will absorb all the other colors coming in from the sun, from that white light, and will reflect back only the wavelength of the orange color. And that's what our eye captures and perceives as the color orange. In video, our primary colors are RGB, red, green, and blue, though in reality the real primary colors are red, yellow, and blue, not green. But in the digital world and in the analog video world, green has been substituted for yellow to give us RGB. The absence of these colors, red, green, and blue, will give us black. And the combination of these colors, red, green, and blue, will give us white at their most intense setting. I'll explain that in a bit. The combination of blue and red will give us magenta, the combination of blue and green will give us cyan, and the combination of green and red will give us yellow. These are the complementary colors, yellow, cyan, and magenta. RGB is an additive form of color representation. We need to add green, add red, and add blue to get the colors that we need. We never add cyan or yellow or magenta. We just add green, red or blue, or we subtract them from the mix. Like if we subtract red, we end up with cyan. If we subtract blue, we end up with yellow. If we subtract green, we end up with magenta. I'll explain this a little bit further in just a bit, but I need to cover one more thing. Bit depth. Now, don't focus on this too much for now, but let's just understand that the smallest measurement of data in a computer world, in a digital world, is a bit. RGB, standard color RGB, what you see on your monitors and on your phones, is made up of 8 bits per color channel, which means that there are 8 bits in red, 8 bits in green, 8 bits in blue. Every bit has 2 possibilities. It's either a 1 or a 0. It's either on or off. That's just how data works. Don't worry about it too much. I'll explain that in another workshop. When we say 8-bit color, this means that every color has 8 bits of data in it. This means that 8 red bits, 8 green bits, 8 blue bits. So because in each bit we have 2 possibilities, it becomes 2 to the power 8. Which basically means 2 times 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 2. Okay, enough there. Basically, it's 2 times itself 8 times, which will give us 256 possible color shades in each channel. So, that's 256 possible color tones in red, 256 color tones in green, 256 color tones in blue. If we multiply all these channels, RGB, so that's 256 times 256 times 256, we get 16,777,216 color possibilities when we combine them together. Like I said, the absence of red, green, and blue will give us black. So red is set at 0, green at 0, and blue at 0. Now if I increase the red bar here, notice how it starts giving in a bit more of that red tint from a dark red all the way to a bright red at 255. There are 256 shades, but 0 here is counted as the first shade. Now, if I decrease that back to 0 and take up the green, we get the same thing, 256 shades of green. And 256 shades of blue. Now, when I increase red, I'll end up with magenta, which is one of the secondary colors. If I take green all the way up, so we have 256 values of red, green, and blue, we end up with white. Now, if I take down the red all the way to 0 and just keep green and blue, we end up with cyan. And if I take up the red and remove the blue, we end up with yellow. So the combination of these 2 colors will give us yellow. That's the other secondary color along with cyan and magenta. So we can get any color we want by mixing these 3 values of red, green, and blue. As I was saying before, if I reduce blue, we end up with yellow. If I subtract red, we end up with cyan. And if I subtract green, we end up with magenta. We need to add green to get back to white.
So how does that translate into cameras? Well, cameras don't exactly see white exactly as we perceive it. Our eyes are accustomed to adjusting to what is white and what is not white. Cameras are not. Cameras need to be told what is white. So I'm going to demonstrate with 2 cameras here, a 7D, which is this camera. The 7D right now is set to 5,200 Kelvin because I have 3 lights over here which are set at 5,600 Kelvin, which is noon daylight. Whereas the PMW 200 is also set at 5,600. You can tell by looking at the lower screen there, it says 5,600 Kelvin. So I'm going to take down the temperature of these lights now to 3,600 Kelvin to show you the difference. The colors now feel warmer, right? It's the same with the 7D and the PMW 200. It's a lot warmer. But that's only because we have told the all the cameras here that the color temperature we're using is 5,200 Kelvin. So if I show you this piece of paper, it looks white, but it's a bit on the yellow side, right? That's because if my camera color temperature is set at 5,200 Kelvin and my lights are at 3,600 Kelvin, over there at the noon daylight where it's 5,200 Kelvin, that's what I've told my camera is white. So anything I add to that will be yellow. The opposite is true, and I'll demonstrate that in a second. Now I've kept the main camera over there at 5,600 Kelvin, just to compare between the two other cameras here. So this is the BMW200 at 3,600 Kelvin, and that's the 70 at 3,600 Kelvin. Now if I take up this piece of paper, you can see that it looks like it's white, right? I'll go back to the other camera. Looks white, right? I'll go back to the main camera, and you can see the difference now, right? So going back to this, what white balance does is it tells the camera where white is between green, red, and blue, and it subtracts or adds blue or green or red to achieve the colors that we need. Notice that the opposite of green is magenta. So if I subtract green, I'm going to end up with magenta. The opposite of blue is yellow. So if I subtract blue, I'll end up with something more yellow. And if I subtract red, I'll end up with something more cyanish. So how does that translate into white balance again? Now, I can set my white balance manually, as I did with the BMW200 and the 7D, by just changing the Kelvin on it. But I can also change the presets. Or what I can do is I can take up a piece of white paper and balance the white on it automatically. This is not the same as auto white balance, which you should never, ever, ever use, because if you move from one place to another or in the same room itself, the colors might change and shift, and you don't want that. What you want is consistent colors, and to have consistent colors, you need to balance your cameras to white properly. And to do that, I'm going to demonstrate with a white piece of paper. Now I'm going to throw the white balance of this camera off again, just so that you can get an idea. I'm going to take it back up to something high. I can't actually see the monitor right now, but let's say this is it. All right? So what I need to do is get a white piece of paper and make sure that it is where my subject is going to be. This is where the lights are hitting. My lights are not hitting over here. That's not where my subject is. My subject is over here. So this is generally where I need to make sure that I make my white balance. If I take this paper and put it right in front of the lens, like this one here, like that, that's not going to help. That's the wrong way to do it. So the proper way is to have a white piece of paper where your subject's going to be and white balance on it. You don't need to have it in focus. You just, with a 7D, all you need to do is just take a snapshot, then go into the menu and go to the red section, which is the camera section, and say custom white. And now select this and say set. But we're not done here. We also need to change our white balance type from the manual setting to the custom setting. Now when I exit, notice how everything's back to white. You see the difference before and after? Same thing for the BMW 200. And then zoom in on the white and click on the auto white balance and move out and see how my colors are back to normal, right? Now I know it says here 3,300 Kelvin, but sometimes it will vary. That's why we take a piece of paper, a white piece of paper, and balance our white on it. Because you can be a fraction or a bit off if you set it manually. So I'm going to try and show you how different colors will affect your white balance. Now I've put a magenta gel over the white piece of paper over there, and I'm going to zoom in on it and click my white balance. What do you think is going to happen now if I zoom out? Is it going to be natural white? The white piece of paper is because it has a gel on it, but everything else will look green. That's because we added green. We don't subtract magenta because it's not a primary color. Green is a primary color, so we added green to reduce the magenta and make the white piece of paper look white. So we ended up with an image that looks greenish. So this time I'm going to balance my white on green. What do you think is going to happen now? Everything looks magenta-ish. That's because we subtracted green and we end up with magenta. Now you notice that the white piece of paper didn't exactly go white. That's because I used a very harsh kind of green, and that's not going to change much, but see how everything else became magenta. Now I'm going to place a cyan colored gel over my white piece of paper and white balance again. What's going to happen when I zoom out? Things look a bit more reddish. That's because I added red to eliminate the cyan and push it more towards white. And now I've placed a red gel over my white piece of paper. What's going to happen when I press white balance? I'll zoom out. As you can see, everything has turned cyanish. That's because I subtracted red and ended up with cyan. I pushed my white towards cyan. Now I've placed a blue piece of gel over my white piece of paper, and I'm going to white balance. I'll zoom out. And yes, everything's now yellowish. Again, that's because I subtracted blue, so it pushed everything towards yellow. Watch what's going to happen when I white balance on an orange gel on my white piece of paper. Everything becomes more blue. That's because I added blue to eliminate the yellow and push it towards that white center over there. So now with my lights at 3200 Kelvin and my white balance on this camera set to 3200 Kelvin or 3300 Kelvin as the camera is saying, I have natural colors, right? You can see me in good proper color. But what if I change these lights back to 5600 Kelvin because they're at 3200 Kelvin right now? What's going to happen? 5200 Kelvin is more towards blue. So it's going to add blue, and I'm going to end up with an image that's more blue because my camera is set at 3300 Kelvin. Watch. There, you see? Now if I switch back to the main camera, you'll notice that it's properly balanced. That's because it is set to 5600 Kelvin rather than 3300 Kelvin as this camera is set to. So why is this important to know and understand? Well, if you don't get your colors right, you're going to end up with bad colors. So some of you might be thinking that, yeah, but that's what I'm looking for. That's the kind of color I'm looking for. Well, yes, that is, but maybe. Sometimes what we try to do is get the right colors first, and then we change and play around according to mood and whatever you need, right?